Good morning or good afternoon to everyone joining us from around the world, and welcome to VTS Young Professional webinar. I'm Shadliya Ben Naila, Secretary of the VTS Young Professional Committee and Coordinator of the Young Professional webinar series. Today we are pleased to host Dr. Ubaid Qureshi, Assistant Professor at the University of Kashmir and a PhD graduated from IIT Delhi. His work focuses on AI-driven technologies for electric mobility, smart energy systems, including EVs, charging infrastructures, digital twins, and smart grids. He has strong research contributions, multiple academic awards, and is actively involved with IEEE in the power, energy, and vehicular technology communities. We are excited to hear his insights on mobile charging stations for electric vehicle charging, optimal routing, scheduling, and grid-aware operation. So please join me in welcoming Dr. Qureshi. So the floor is yours now.
Thank you, Dr. Professor Ben. Thank you. And thanks for the generous introduction. Thank you so much. First things first, I'm Dr. Ubaid Qureshi. I'm an assistant professor in Department of Electrical Engineering at University of Kashmir. I recently graduated from IIT Delhi, where my specialization is electric vehicle charging and large-scale EV mobility. So let's directly go to my presentation. Professor Ben, is this visible?
Yeah, it is. Yeah, it is. Okay. Please go ahead.
Okay. So in today's webinar, we are going to discuss the mobile charging stations for electric vehicle charging, the optimal routing, scheduling, and grid-aware operation of these mobile charging stations. First things first, since we know that world is experiencing rapid growth in EV charging demand, grid integration of renewables, and distribution level stress. Since the EV users are increasing day by day, so EV charging demand or EV load on the grid is increasing. At the same time, there has been a lot of development in last decade in the grid integration of renewables, be it the solar energy, be it the wind energy, be it the other renewables forms of energy. This leads to stress in the distribution grid. Why? Because all these renewable energies, which are usually the rooftop connected as well as the EV charging demand, they are connected to the distribution grid. This leads to the stress on the distribution level of the grid. This has created four main challenges for the grid operators worldwide. Number one, the overload. Since we know EVs and renewables strain local distribution lines, causing local congestion and feeder overload by uncontrolled EV clusters. Number two, the wobble. Since the load shifts and uncertainty lead to reactive power imbalance and voltage deviations. Number three is the wild card. Since there is the combined uncertainty of both solar, wind as well as EV demand, and that makes the forecasting a nightmare for power grid operators. And the number four is the constraint. At present, we lack fast, flexible grid support assets to quickly balance the generation and demand for the power grid. So in this webinar, we'll be discussing the research directions that address all these four challenges. So what is the goal? What do we want to do? Actually, the aim is to convert EV charging from a grid stressor into a flexible grid support asset. The first question that we need to answer here is it possible that we can use EV charging from being a grid stressor into a flexible grid support asset? The answer is big yes, we can do this. So in this webinar, we are going to investigate and will provide the solutions to the problems of electric vehicle charging on all the four fronts. Let me give you a brief perspective how we go about electric vehicle charging. Initially, when we started this electric vehicle charging, the charging used to be the in-house, what we call as the residential chargers, or what we typically call as level 1 charger. In the level 1 charger, you used to come home, you used to plug your EV to the charger for overnight, and tomorrow till tomorrow morning, your vehicle used to be fully charged. But the problem with this is you need substantially large amount of time to charge your vehicle. It used to take considerable around 10 to 12 hours. As the charging technology developed, in today's world we have fast-paced level 3 DC-DC chargers which can charge your EV in a very small interval of time from around 15 minutes to from around 15 minutes, 30 minutes or at most around 1 hour. What we call as commercial fast charger. It's not possible to install these commercial fast chargers at your residential place, obviously because it's not going to be economical. It's not going to be possible to install them at home. They're at a very high voltage, so we have these commercial charging stations coming up around the world, just like we have commercial gasoline refilling stations for the gasoline based vehicles. So when we try to solve this problem of EV charging, we try to solve this problem on the four fronts. Number one, we try to optimize charging scheduling in a commercial charging station. We found out there are a number of inefficiencies in this commercial charging station where people take their vehicles for charging. This is just like the conventional gasoline based refueling station where we take our gasoline based vehicles for refueling. Similarly, we have these commercial charging stations with fast level 3 chargers where you can charge your vehicle very fast. But what we observed is that there are inefficiencies in these commercial charging stations, and if we can improve, if we can schedule effectively the charging in these commercial charging stations, to some extent we can reduce the stress on the grid. In fact, we can support the grid to some extent by supplying energy back to the grid using the concept what we call as V2G, vehicle to grid support. Next, what we found out that there is also scope where we can use these electric vehicles to participate with other distributed energy resources and together form what we call as virtual power plants. When EVs combine with renewable energy generators, together we call them as virtual power plants, where these EVs help these renewable energy generators by making available the battery available in the EVs for storing energy in batteries and then supplying the energy to the grid during peak load times. What this means? This means that EV supplies the battery, renewable energy provides the intermittent renewable energy. Together, you have a system which can supply energy to the grid in the most efficient manner. In fact, the battery of the EV, by providing the battery, these EVs can make these renewable energy generators to participate in the market, power grid market as well. Number three, these are the two ways. Number three, what we found out that there is one more way in which we can control the electric vehicle charging so that it is efficiently charged and electric grid is not stressed. And what is the third way? Third way is to use the pricing scheme. We all know that we can basically manage the demand and supply by dynamic pricing. So we introduced here a novel type of pricing scheme, what we call as menu-based pricing scheme. And this menu-based pricing scheme, we use the Stackelberg game theory to basically arrive at the optimal pricing, where we formulate the problem if you want to maximize the social welfare. So if you want that more and more people should adopt EVs, we can set the pricing for the social welfare. If this is being run by a private entity, they'll definitely be interested in maximizing the profit. And if it's being operated by a government, so they'll try to maximize the social welfare. And finally, we developed a charging scheme different from the commercial charging stations, what we call as mobile charging services. When we introduce this concept, in this concept, you don't have to take your electric vehicle to the charging station, but you request the electric vehicle charging services from your home, from your office, from your workplace. You simply use your mobile phone. You have an app over there. You request that I need this much amount of charge by this time. We have these mobile charging vans. They will come directly to your place wherever you have demanded the energy. They'll come there, charge your EV, and charge you accordingly. So you don't have to take your vehicle anywhere. You don't have to spend the additional time. And in addition to that, the main problem that we are facing today in the commercial charging stations is the problem, basically two problems. One is the problem of congestion. Since I already told you that it takes considerably large time to charge an EV, even with today's fast level 3 charger, it takes around 30 minutes to charge an EV. If we compare this to a conventional gasoline based vehicle, it takes only a couple of minutes to refuel it. So even if we have 10 chargers in a commercial charging station, that means in 1 hour, it can only charge 20 vehicles. If you compare this to the gasoline based refueling, a gasoline based refueling can a gasoline based refueling station can refuel around 1,000 vehicles in 1 hour. That is, since we take large amount of time to recharge an electric vehicle, there's going to be huge queue, huge line in the public commercial charging stations, which will basically discourage a lot of people in adopting electric vehicles. But we want, on the contrary, we want that more and more people should adopt electric vehicle for the clean transportation. In this mobile charging station, since you don't need to take your vehicle to the charging station, in fact, the charging station, these mobile vans carrying the fast level 3 DC-DC charger and the battery bank will come directly to your place, to your office, to the parking lot, charge your vehicle and go. This also means you are also solving one more problem, and that is the problem of the range anxiety that these EV owners face today. The range anxiety is the problem where you're not sure, you're not certain whether you will be able to complete a trip from one city to another city without being run out of the charge. By using this mobile charging service concept, even if you feel that you're facing that you have less amount of charge in the EV, you can request it in between the trip. These mobile charging vans will come, they will charge your vehicle over there, give you additional charge, and you can easily go from one place to another. So finally, what is the main outcome of today's webinar? I'm going to introduce you to deep reinforcement learning based real-time routing of these mobile charging stations for both congestion elevation at commercial charging station as well as the reactive power support. Together, these four contributions form a unified architecture to turn EVs from a load to a flexible resource. Okay, this is the first front that we are trying to solve the problem from. The multi-objective optimization, the multi-objective para-to-optimal optimization problem in a commercial charging station. Let's consider a typical case. In a commercial charging station, we have a number of vehicles, EVs coming in. We have a charging operator here, charge controller over here. This charge controller has energy available from renewable energy, conventional energy that is from the grid, as well as it has some limited energy storage available. This charging controller want to maximize the profit. How can it maximize the profit? It can maximize the profit by charging different EVs using maximum amount of renewable energy. Also, even if it needs, which it definitely will, when it needs to take energy from the conventional grid, that is when it needs to take energy from the grid, we want that it should take energy from the grid when grid is not running at its peak load. That is during the daytime or during the night, not in the mornings, not in the evenings when we have the peak load running on the grid. Why? if you want to take more load from the grid during the peak time, since the grid is already stressed, you don't have sufficient energy available. So what grid operators do, they price electricity at a higher price, what you call as dynamic pricing, during the time of peak load. So if this grid charging operator, charging controller need to take energy from the grid during the peak times, it will have to spend more money. If it have to spend more money, so charging will be costlier. So, but what we want to minimize the price of charging. We want to make it as efficient, as economical as possible, while at the same time preventing our grid from being overloaded. So in this case, we have a number of electric vehicles connected to different chargers in the grid. We have a number of EVs idle. When a new electric vehicle arrives at the when the new EV arrives at the charging station, the EV owner submits her vehicle to the charging station and specifies that she need her vehicle to be charged by this time. She needs this much amount of energy in her vehicle, and in response, the charging station operator has to decide. Now let's try to understand the problem from the perspective of the charge controller. The charging station operator will have to decide, how should I charge these EVs where I don't know what future EVs are going to come, what is going to be their demand, and what is going to be their deadline. Also, one more uncertainty this EV charge controller faces is that though she may want to use maximum amount of renewable energy, but she does not exactly know what is going to be the renewable energy available at different instants of time. Though she has a forecast available, but as we know, forecast is only forecasting. Yes, we can only have an estimate that we will have this much amount of energy available, but it's not going to be the exact value. Fine. Similarly, we are going to have an idea that we may have this much number of vehicles coming during this time interval, needing this much amount of time. We have the idea, we have the estimates, but we don't have the actual numbers. And when you want to perform the optimization problem where you want to minimize the cost of charging, when you don't know that whether you are going to have the particular value of renewable energy, what is going to be demand and deadline, that is, you have uncertainties available. You call such type of problem as solving an optimization problem in presence of stochasticity or uncertainty. This forms a different type of a problem where you have to solve problems subject to uncertainties as well. You don't have anything, nothing is over here certain. Most of the things, in fact, here are uncertain. So, how do you formulate this problem? We formulate this problem as a multi objective Pareto optimal convex optimization problem. One more thing, we could have solved this problem using, say, genetic algorithms or any evolutionary method. But the thing over here is, this charging operator needs to solve this problem at regular intervals. Say every 15 minutes, the charging operator needs to solve this problem to make sure that all the EVs are charged by the deadline, electric grid is not stressed, you're not making too much change in the charging schedule, while at the same time you have to minimize the cost of the charging. But this problem has to be solved in the real time. Why? Because you have to perform this problem regularly every 15 minutes, every scheduling interval. So how do we do this? Can we use the evolutionary algorithms? Answer is no, because it takes time to solve evolutionary algorithms. So we formulate this problem as a convex problem. Convex optimization problems are a special type of optimization problems which guarantee the global optimal solution. If you are able to solve these problems, you find the solution is the global optimal solution, and you can solve these problems very fast. That is, you can solve these problems in a real-time manner. That's why we formulate this problem as a convex optimization problem. So what is going to be the output solution of the optimization problem? The charging operator needs to know at which instant of time which of the vehicles need to be charged, which of the vehicles should I keep idle, so that by the deadline of each vehicle. Every vehicle is charged, satisfied, and while we are minimizing the cost. How can we minimize the cost? By maximizing the use of renewable energy. So how do we do this? Since there are a number of uncertainties involved here, we use the concept of maximum likelihood distribution estimation, what we call as MLDE, maximum likelihood distribution estimation. And for obtaining this MLD, we are using a special type of neural networks, what we call as mixture density neural networks. Unlike the traditional neural networks, these mixture density neural network have incorporated in them, they inherently model the uncertainties in the system. Since we have a lot of uncertainties available, we cannot use the neural network. If we use the simple direct neural network, it will provide us the particular value of what is going to be, say, the renewable energy available in different instants of time. But as I already told you, we're not certain if you're going to have it available or not. So what is the best way to do it? The best way to do it is not to use the exact values, to somehow model the uncertainty into the model itself. We model the uncertainty into the model so that our solutions are as close as possible to reality. So we use this mixed density neural network. They give us the mean and standard deviation from the training data. So when we use this mean and standard deviation, you don't use exact values. You randomly sample from this distribution and perform the test on different values so that our model gives the our model gives the best possible results available. Second front, this was the first one where I told you we need to optimize. Since we found out there are large number of uncertainties, there are large number of inefficiencies involved in a commercial charging station. So we try to reduce those inefficiencies. We try to omit those inefficiencies. We try to make our system as economical, the best possible, what you call as the optimal operation of the commercial charging station, where we maximize the renewable energy. So that was the first case. Number two, what else can we do to make these electric vehicles fit into the power grid? What is the second thing we can do? The second thing, as I already told you during the introduction, is the virtual power plant. We make these EVs to be part of virtual power plant. Now let me give you a brief overview of what we are trying to do over here. Suppose we have the renewable energy generator here, the wind farm over here. As you can see in the slide here, we have the wind farm over here. If this wind farm wants to participate in the electricity market, if it wants to contribute energy to the grid, but the problem in contributing energy to the grid is this wind farm is not certain of the amount of energy it's going to generate tomorrow, day after tomorrow. So it cannot commit that it's going to provide this much amount of energy because it's not certain whether the wind energy will be available or not. The amount of wind will be obviously available, the amount of energy it can contribute. So how can we solve? At times, say for example, if you are committing that you are going to supply 100 megawatt of power to the grid, but the thing is, at that time you have 120 megawatt available, so you have surplus 20 megawatt. But at the same time, next interval you are supposed to supply 100 megawatt, but you have only 80 megawatt available. But the thing with the power grid is you have to balance the energy and the demand on the real time basis. Now, how do you solve this? How do you solve this? How can we solve this problem? The answer is if we somehow could store this energy in the batteries, if we have some storage available, then you can schedule it in the best possible way. Why? At times when you have the energy available in surplus, you store it in the batteries at intervals. During the intervals when you have the energy deficit, you can take energy from the battery and supply to the grid. That means you can participate in the market efficiently because you have energy available. Now the question from you, how is it possible? Is it possible to have this much amount of power bank available within these wind farms so that you store energy in the battery and then you supply to the grid? Answer is no. You cannot have this huge a battery bank to store this much energy. Then we need to find out, is there an alternate way where we have battery storage available and this battery keeps on idle for some part of the time? The answer is yes. And we have this energy available. Sorry, we have this battery available in the EVs. Since EVs have a considerably large amount of battery bank available, we can store a good amount of energy in EV. Do we need one EV? No. Two? No. We need a fleet of EVs. That is, if these electric vehicle owners, these EV owners, participate with this wind farm and they together form a cluster, and this together, the combination or the partnership of the two, renewable energy, in this case I have considered the wind farm, and the EV battery, we together call it a virtual power plant. If they have a scheme among themselves that wind energy generators, the energy they generate during the time they have surplus energy, they can store this energy in the battery of the EV. And then during the time it needs to supply the energy to the grid, they can together supply energy from both the battery of the EV as well as to the grid and supply it, uh, as well as the wind farm and supply it to the grid. That way you can basically maximize your profit. But the question is, why would EV owner let her battery being used by virtual power plant or the wind farm? What does she earn? The answer is energy credit. Since the EV battery owner allows the wind farm to store energy in the EV battery during the times when EV is staying idle. For example, during the day, we are busy running from one place to another, from the office, from the university. During night times, most of our vehicles sit idle at home. If we can connect this to the virtual power plant, this virtual power plant operator will store energy in my EV, and then during the time of high price available in the grid, it can supply energy to the grid, making profit. What will I get? The answer is, I will be provided the energy credits. That is, if the wind farm stores suppose 100 units in my EV battery, it will take back only 80 units. I will get 20 units free. That is, you don't have a kind of scenario. You don't have to spend any money on charging your EV. Why? Because since you are letting the virtual power plant operator use your EV for storing energy, in return, they provide you some amount of units free of cost, say 20 units per 100 unit, that is 20%. So you run your EV in the day free of cost, you don't have to spend anything, and your vehicle is charged during the night. So we call this as the virtual power plant. And this virtual power plant, then this wind farm decides how to basically, in the optimal manner, supply this energy to the grid because it wants to maximize the profit. Now the obvious question is, when should it supply energy to the grid? The answer is during the time of the peak prices. When grid is running on the peak load, there is deficient generation kind of and surplus load. So prices are high. If you can supply energy during that time, since you can sell your units at a higher price, you are making a lot of profit and overall contributing for stabilizing the grid as well. So this is the second front where you can use EVs to basically make your system efficient and smarter. Number three, as I told you during the introduction, we have introduced a novel scheme of charging where we have introduced the charging as a service scheme. We call this mobile charging service. So what is this mobile charging service? Mobile charging service refers to a system where we have specialized vehicles equipped with charging equipment. Like we have the vans, they have the fast level 3 DC-DC chargers available, and these vans can travel anywhere wherever the demand arises. This service provides an alternative. Not here to replace fixed charging stations, no way. But in addition to fixed charging station, you can use the mobile charging stations. This helps in a number of ways. How? They offer flexibility because you can charge your vehicle anywhere. You just request the charging and we'll send the mobile charging vehicle to your home, to your office. Even on the highway, we will send it. Number two, the convenience. And number three, the most important thing, you are basically decoupling the EV load directly from the grid. I'll try to explain it in a simpler words. Since most of the EV users, as per the research, most of the EV users who will charge their vehicle in a commercial charging station tend to charge their vehicle during two times mostly. Either in the morning before going to the office or in the evening after coming from the office. But we all know both during the morning bracket, the morning time period, as well as the after office evening time period, they both are the peak loads for the grid. Why? Because your domestic loads are at peak during this time. So you would not want that most of the vehicles are connected to the grid during the peak times, neither in the morning nor in the evening. Why? Because it will stress your grid. You will have to have additional generation. And that generation is going to be idle then after the peak period of time. That is, your load curve is going to be poorer. You will not want your load curve to be poorer because poorer load curve means high cost of generation. High cost of generation means you will have to get that revenue, so that means high cost of energy. But as engineers, we would want that the cost of energy should be as minimum as possible so as to make it affordable. Using this mobile charging concept, you are basically decoupling this EV load from the grid. Why? Because these mobile charging stations are not directly connected to the grid, though they are charged from the grid, but they charge their battery during off peak times, that is during the day or during the night. Then they can charge your EVs at any time, say during the day when you are working in the office or during the evenings when you are at home. But there is no problem. Why isn't the problem? Because you're not connected to the grid. The energy is already stored in the battery of the mobile charging stations. That is, we have decoupled the two. So number one is the flexibility. Mobile charging stations can be deployed to various locations based on demand. You find demand is somewhere more, you'll schedule these mobile charging stations in that place, providing charging solutions where fixed charging stations may be sparse or unavailable. So it works in those areas as well where yet EV penetration has not been that much. Convenience. They offer on-site charging, allowing EV owners to charge their vehicle without having to travel to a fixed charging station. It saves time and it saves effort. Reduce charging costs, since mobile units eliminate the need for extensive physical infrastructure and installation cost instead with fixed charging station. You need not install fixed charging station at home. You can schedule the energy and will supply it at your place. By bringing the charging to the customer location, mobile charging service improve overall convenience and satisfaction, particularly in urban areas with high charging demand. Next is scalability. This model is scalable. This is just like we call our Uber. You use the mobile app to book the Uber that I need to travel from this place to this place, and then you have to choose which vehicle you want to use and go. Sorry. It is scalable. You can start with 10 mobile charging units. You can scale it up to 100 to 1000. As the demand increases, you can increase the number of mobile charging vehicles. So you don't have to initially invest in the infrastructure much. Now, what is this menu-based pricing concept? What are we trying to do in the menu-based pricing concept? This is a very simple concept. I like it I like it a lot. So in this case, what happens here? So you are booking this mobile charging station. So you will open the app. You'll have the UI interface, desktop client or the mobile app. You'll open the app. It will take your location that you need energy from this location. You need energy at a particular point. So for example, in New York, you require energy at this place. Next, you'll have to specify how many units you need, what amount of energy you need, and by what time you want it. You have to specify the location. Number two, you have to specify the amount of energy. Number three, you have to specify the deadline by which you want your vehicle to be charged. When you enter the three, you will get a list. You will get a menu. In this menu, what we will provide you that if you want these many units of energy by this much time, you will have to pay this much. If you want this, just like we have in the restaurants, if you require this much amount of energy by this deadline, you will have to spend this much amount of money. What we are doing this over here, uh, when we formulate as mobile charging service operator, when we design the menu in such a way that we are prioritizing those menus which are best for the grid, which are best for maximizing the profit. By doing so, when EV owner sees, suppose she's getting 10 units of energy in 1 hour, say for $10. If she's getting 20 units of energy in 1 hour, say $12, she will definitely have maximum utility for getting 20 units in 1 hour for only $12. That is additional 10 units for $2. This is one of the example I'm just giving. That is by making some of the options in the menu having most maximum utility for the user will tend to take that menu. Fine. So what we here do, we here find out what is the cost incurred by the mobile charging service operator. We keep little bit profit and then pass on the cost to the electric vehicle owner. This is how we design the menu based pricing. So what we are doing over here, by designing the menu, you are basically making those options in the menu lucrative, which are best for the grid, best for maximizing profit. We can formulate this problem for three cases. One of them is the social welfare maximization. You can formulate the problem such that we maximize the social welfare. Maximizing the social welfare means we want to maximize the utility or maximize the marginal cost as well as the consumer surplus. That is, we want that both the service provider as well as the end consumer, they're both having the maximum utility. Number one. Number second is the profit maximization, where we are not maximizing the consumer surplus, we are only maximizing the supplier surplus. So you call this profit maximization. This type of problem is people who are running the private organization or private operators who are running these mobile charging operations or mobile charging stations, they'll be interested in the profit maximization. Governments will be interested in social welfare maximization. And there is one more, we call this value-based pricing, where we have a fixed amount of profit for each of the requests that we supply. So you're kind of trade off between the two. You are making both of them happy at the same time. These are some of the results where we have tried to show that how it improves the social welfare, how it reduces the number of EVs required, number of mobile charging stations required, how it maximizes the number of EVs being charged, and so on. And this is the last thing. Finally, a distributed route. We call this deep routing. Now, let me give you a first background behind this, what we are trying to do now. Now, suppose we have these mobile charging stations, and these mobile charging stations need to be serviced or need to be sent to different EV charging requests. So, for example, I am running this mobile charging service company and I receive a number of requests. When I receive this number of requests, what I have to decide is where should I send these mobile charging stations and in what order so as to have the maximum EVs being charged, in fact, all EVs being charged while reducing the cost. The problem here is this is the typical optimization problem. Suppose I have given here the toy problem. You have number of EVs available. You have an EV in zone BA, zone B, zone D, zone F, E, G, and H. But you have only two mobile charging vehicles. Presently, one is at zone B, one is at zone G. You need to decide which of the EV charging requests can be serviced by mobile charging vehicle 1 and which of the EV charging requests will be serviced by mobile charging vehicle 2. Obviously, what you will want to minimize the cost of charging. Cost of charging should be as minimum as possible. While at the same time, you want to maximize the utility of the users. You want that EV user should have the best possible experience. You don't want to miss any charging requests, but you want to minimize the cost. Routing of this vehicle to different locations or routing of this vehicle to different locations, this is the classical problem in mathematics, what we call as combinatorial optimization problem. You cannot solve such problems directly, and you cannot formulate this problem as a convex problem. This is a typical combinatorial optimization problem. In fact, when we formulated this problem, we found out that this combinatorial optimization problem is actually combination of two NP-hard optimization problems. One is the bin packing problem. Number two is the multi-city traveling salesman problem. These are both two combinatorial optimization problems. And this problem that we are going to solve over here, this is the combination of two NP-hard combinatorial optimization problems. So now, how do you solve this? How can we solve this problem? How is it possible to solve this problem? Is there a way to solve this or not? How can we solve this problem? We cannot solve this using convex optimization. You cannot formulate this as a convex optimization problem. So then the answer is we can use the evolutionary algorithms. We can use, but the problem here again is we want to solve this problem in real time. We have to solve this problem in the real time. How can we solve this problem in real time? How to solve this problem in real time? Combinatorial optimization problem is NP-hard. That is, as the number n increases, it becomes intractable. You cannot solve this in real time. So what we use distributed reinforcement learning, where we use the DQN algorithms to formulate this problem as a reinforcement learning problem. And then we solve this as a reinforcement learning problem using the DQN. Since we train the agent and then we deploy these agents in the real world setting and they can go about charging the EVs easily. This gives the schematic of the overall schematic, what basically we try to do over here. For those of you who are not aware of the reinforcement learning, in reinforcement learning, it's a type of unsupervised learning. In this, what happens? This is the same way in which a child learns how to walk. You have an agent. That agent takes some decision. When it takes some decision, it gets a reward from the environment. You have an agent. You have an environment. The agent takes some action in the environment. Environment gives some reward. While taking the reward, this agent again takes an action, again gets a reward. The aim of the agent is to maximize the reward and learns from this action reward thing. It continuously tries to update the action so as to maximize the reward. So in this case, what we are doing over here is we have an agent, which is a DQN agent. We train this on the model. And the good thing about this is the model free learning. We don't need the model. You don't need the model of the road and all. You just take the action. It will learn of its own by taking the action, by getting the reward and try to maximize that reward. So you have the agent over here. We have a dispatch center over here. Dispatch center decides which MCV will go to which EV request. So it has dispatch center decides which MCV goes to which EV and in what order, which EV will its service first. You have to consider all the constraints as well, since these all the EV owners have different amounts of energy needs and different deadlines. We have the road network model in this. Using the road network model, you try to get the estimate of the times it will take for MCV to travel from one zone to another zone. Similarly, in order to make our scheduling or routing efficient, we use the future EV charging demand estimation. We have an estimation that in this area, in this time, during this part of the day or during this day of the week, we are going to have this much amount of demand. So accordingly, we dispatch our MCV to that area in anticipation that we know that demand is going to be high. So what happens here? This MCV, we first train this this agent. We first train this agent. It gives an action that is dispatch center sends MCV to EV. So if you are able to satisfy all the demand in a particular area and minimize the cost of the travel, minimize the number of MCVs required, you consider that as a good reward. So it gets reward. It updates its policy that this policy was good. So next time it will try to, even if it will try to adjust the policy, but it will try to use this policy more often. This is how we learn this. Once this agent learns it completely, then we deploy it in the real world setting where it solves the problem on the real time basis. So this is, I'll not go too much into mathematics and all. This is the reward function. In the reward function, what we are trying to minimize, we are trying to minimize 4 or 5 things. We are trying to minimize the energy mismatch. We are trying to minimize the time mismatch. We are trying to minimize the load on the grid. We are trying to minimize that MCV should not run out of the charge, as well as we are trying to minimize the miss ratio. And we use the discounted reward function overall to train our model. We are using the famous Bellman equation for the DQN agent. This is how our agent learns over time. These are some results. So overall, what we presented in today's webinar, we have approached the problem into divided the problem into 6 pillars. We use the mixture density neural network for the forecasting. We use the convex optimization for EV scheduling. We can use the Stackelberg game theory for shaping the demand. We use mobile charging service for on-demand charging. Finally, we use distributed deep reinforcement learning for real-time routing. It does definitely have an impact on the grid. You can, in fact, for the future, you can also take this into consideration. We can use these in mobile charging stations since they have the battery bank available with them, as well as the fast level 3 DC-DC charge, or they have the converter. You can use these to supply energy back to the grid. That is, you can help in the congestion alleviation. You can help them support the reactive power to the grid. You can help them backstart the grid. You can help them during emergency. So there are a lot of advantages. In addition to this, these MCVs can provide. These are the results. During the experimentation, we found that in the commercial charging EV station optimization, the charging cost reduced by 16 to 13% versus the online methods without forecasting. We show the MDNN forecasting improved accuracy by 25 to 50%. We show that robust optimization under uncertainty is available, where you have uncertainty in arrival, deadline, renewable variability. Next, during the virtual power plant stochastic optimization, VPP revenue improves substantially when we use EV storage plus MDNN predictions. MDNN reduced cost 11% and improved renewable integration by 9%. The framework scaled effectively with large EV fleets, and it performs close to optimal offline under real-world condition. The experimentation has been performed in the Belgian wind farm. Next, we introduce you to the menu-based pricing. We reduce the number of MCVs, number of charges required. Charging costs drop significantly. We showed that how the parameter kappa can basically help in the peak shaving of the load curve. Similarly, we showed that shift and flexible load automatically without direct control of the EVs. Next, the routing and scheduling optimization. The proposed algorithm charges 65% more EVs for the same fleet. Miss ratio drastically reduced. We require a fewer mobile charging station and less frequent dispatch horizon. We have a better efficiency and lower cost. And finally, the most novel contribution, where we use the distributed reinforcement learning based mobile charging station to route these MCVs in the real time for the grid support. We have active power injection during congestion hours. Reactive power support improves the bus voltage and congestion relief at stress nodes. So what relevance does it have to grid operators around the world? These MCVs can solve the problem of congestion elevation, they improve the voltage stability, they provide the rig to power support, flexibility for the load dispatch centers, they provide the renewable balancing, while at the same time, it's practically deployable. So conclusions, grid stress is reduced, operational flexibility improves, renewable absorption enhances, voltage control is supported, congestion management is being provided by these MCVs, and it provides fast response assets to the grid. We believe that this work is technically rigorous and operationally relevant and deployable as a pilot project for DISCOMs. Thank you so much. Thank you. If you have any questions, please.
Thank you very much, Dr. Ubaid, for this webinar and the very insightful, actually, presentation. And I see that we have one participant in the floor, so I will be happy to open the floor and give him the floor if he has any question. I'm not sure if he does hear us. Furqan? At the moment, I don't see any reaction from him. I don't know. So, meanwhile, I have a question for you, Dr. Ubaid, please.
Sure.
So, I will start with the following question. Can you please display one more time slide number 4, please? Yeah. So my question is, what is the multi-objective optimization function based or use, sorry, for commercial EV charging scheduling? If you can explain further, please, about that.
Yes, actually, when we solve the optimization problem in a commercial EV charging station, you don't have a single objective. You have a number of objectives, and the number of objectives are conflicting in nature. So, for example, you want to minimize the cost. This is one of the objective in a commercial charging station because the charging operator will definitely want to minimize the cost of the charging. But at the same time, you have the deadline and energy constraints from different EV operators. You want to respect and you want to satisfy those constraints as well. So in order to formulate this problem as a convex optimization problem, similarly, you have constraints from the grid as well. You cannot draw energy from the grid during peak period of times and stress the grid beyond a certain limit. So since these objectives are conflicting in nature, and when we have a conflicting objectives in nature, and when we formulate the problem, if you formulate the problem as MILP, mixed integer linear programming, then you cannot solve the problem in real time. So in order to formulate the problem and solve it in the real time, we basically introduced or incorporated these constraints in the objective function itself and formulated a unified objective function where you have a number of constraints added into the objective function, but the overall problem formulated as a convex problem. When we have a convex problem, we can solve this in the real time using any of the convex optimization problem solver. So for example, I have been using the CVX by Stephen White from long time. So you a very robust method of solving, and you get the solution in real time, and you are guaranteed the global optimal solution.
Okay, thank you very much for the answer to my question. I have another question, please. On page 11, please. Can you show us, please? Yeah. So actually, my question now is about you were talking about the reinforcement method and the use of that. So I would like to go deeper. And my question is the following: how does the DQN-based deep routing algorithm define actually the speed, the action, and the rewards for optimal routing of mobile charging stations? If you can explain further.
Yes, this is the reward function here on the left side. You can see this is the reward function. In the reward function, we have the number of objectives. The number of objectives, we incorporate them into the reward function. So if you attain a particular objective, corresponding to attaining the objective, you get the reward. Similarly, there are some penalties like the negative terms. if you are failing to achieve a particular objective, say for example, the cost of charging. If you have cost of charging more, your reward should be less. So that is why we have introduced those terms over here. Similarly, the negative sign terms. Similarly, if you have the load on the grid, if you have a scheduling policy, and in this scheduling policy you provide the scheduling policy, you charge the EV, everything is fine, but suppose your MCV is running out of the charge in a particular zone. This should not happen. While learning the policy, this agent, if it comes across such a policy, everything is going smooth, but all of a sudden this MCV runs out of the charge. If this MCV runs out of the charge, we should penalize this policy so that this policy is not repeated by agent again. That's why we have introduced the negative terms over here with the penalty factor corresponding to the importance or the weight of the different objectives.
Yeah. Thank you very much for the clarification. I see that we still have like 4 minutes, so if you allow me one more question, please.
Sure, I'll be happy to answer.
Yeah, thank you very much. I appreciate. Can you please go to page 16? Yeah, so here I would like to ask about actually how the mobile charging station can provide grid support services. Can you explain further actually how it's possible?
Sure. Actually, this mobile charging station, it already has a battery bank available with it, and it also has a converter available. So you have both the converter and the battery available. Now, consider the situation. In the grid, you have a particular node, and on that node, you are facing that you have a rake to power deficit, that you need to support the grid with the rake to power at a particular node. Conventionally, what we do, we have these synchronous condensers or the capacitor banks connected to a node where you supply rake to power to the grid. But these capacitor banks are fixed at a particular station. Since these mobile charging stations are mobile, you can send them from one location to another. Wherever you find that you need to support the rake to power, you go to that location, you connect this mobile charging station to the grid, and you support rake to power directly to the grid at that point. The advantage here is it is flexible. So next you find that you need to supply rake to power at some other node. You can basically route this to some other place.
Okay, thank you very much. Actually, I would like to, with 3 minutes, we come to conclude our webinar today. Let me please thank you once more time. Thank you for the insightful and technical rich presentation, actually, Dr. Ubaid Qureshi. Your work actually provided a clear and innovative vision for making EV charging to asset actually to the power grid. I would like just to add a comment that, as usual, the record of our webinar will be shortly available on our VTS YouTube channel, so that like students or other fellow researchers can have the opportunity to look at your presentation and your presented work. Thank you very much, Dr. Ubaid, one more time for your availability today. It was a pleasure having you today. Thank you very much. We appreciate your participation. Thank you.
Thank you, Professor Ben. Thank you so much. I would like to thank VTS Society, our chairman. Thank you so much.
Indeed. Actually, your participation as a young professional ambassador in our webinar was a true insightful webinar. It made actually it allowed us to have a quite interesting interaction, and we could also have a look at your rich and insightful research result. Thank you very much one more time. Wish you a lot of success in your future endeavor. Thank you very much.
Thank you.
Thank you. Bye-bye. Thank you.